Hi everyone, welcome back to CHM421 Analytical Chemistry. We will continue our learning on topic 4, Titrimetric analysis, or another name we call it volumetric analysis. As we know, titrimetric analysis is about titration. In the past, a few videos, we covered the acid-base titration. So now we will learn another new type of titration, which is complexometric titration. So from the name, you can understand that this titration will using the concept of complexation. I hope you heard about complexation when you studied during the SPM or during the Asasi or diploma. You went through about complex compound. Complex compound is the ligand plus with the metal. So in this video, we will discuss in detail how the titration can be carried out by concept of complexometric technique. So complexation is the formation of compound in which the central metal ion is bounded to ligand. Okay, meaning that complex compound we have central metal ion in the center will be bind to the ligands. What is the ligands? We will define the ligands later on. Basically, any atoms, ions, or molecule can consider ligands. But don't worry about it. After this, we will define further what is the ligand. So during the complexation, the metal ion in the center will be bind to the ligands via coordination covalent or coordinate covalent, or another name is dative bonding. So the resulting compounds from the complexation reaction, we can call it coordination compound. So this coordination compound is an organic compound because it's a metal plus ligand. All right. So what is the difference in organic with organic compound? You learn a little bit during you study organic compound. Organic compound normally is involve the hydrocarbon with bond, meaning that they have uh, hydrogen, uh, and also the compound have a lot of carbon. That's we consider organic compounds. But the coordination compound, which is involving metal in the center with the ligand surround it, we call it inorganic compounds. Okay, so coordination compounds sometimes can call it metal complex because it's a complexation. So metal in the middle, we call it metal complex, or in a simple way, we call it just complex. All right. So in here, it's showing the example of ligands. Okay. As you remember on the first slide, the ligands can be atoms, can be ions, or can be molecule. So here is a few example of ligand. Neutral molecule. We have water. We have ammonia. We can have carbon monoxide. We can have nitrogen monoxide, and etc. So in ion also, in ion is ion with negative charge. Anion also can be part of the ligands. All right. So it can be part of the ligands. So in here we have fluorine, chlorine, iodine, hydroxide, or cyanide. CNH, cyanide. So, desirable feature of the ligand. So, what is the properties in order to be a ligand? It must fast reaction with the metal ion. Because why? Because in the complex session, we need metal will react with the ligand. During the titration, complexometry titration, the titration can be done by using metal plus ligand. All right. So the ligands, it should be fast reaction with the metal ion, and the ligand should have large formation constant. So Kf, we call it formation constant. Large formation constant make the molecule highly stable. So the ligand also should showing the uh, sharp change in metal concentration close to equivalent point, because in titration we cannot run away from the equivalent point and also end point. So it below is described a little bit on the KF. Formation constant, stability constant, a constant, or can we call it binding constant. So you can read this one if you wish. So now I further explain what is complex ion, what is ligands, what is dative covalent bonding. So if you remember just now, I said complexation should be metal ion in the central will be bind with ligand. Okay, ligands can be atom, can be ions, or it can be molecules. So now, what is complex ion? So they have a few terminology here. Complex ion, ligands, and also dative covalent bonding. So what is complex ion? Complex ion is in the ion form. It consists of central metal atom or cation surrounded by ligands. Okay. Again, the central complex ion, because of this ion, is consists of central metal ion or cation surrounded by the ligand. So this one we call it complex. The combination of metal ion with the ligand we call it central complex ion. So what is the ligand? Normally, ligands can be in ions or neutral molecule. The most important features isthmus has lone pair of electrons. Ini an ion or neutral molecule, in order to be the ligand, it must has lone pair of electrons. Okay, lone pair of electrons is non-bonding. We call it non-bonding electron. So let's say we said a ligand's neutral molecule. For example, we have H2O. How do we know this H2O have a lone pair of electron? You can draw the Lewis structure. You know this hydrogen, they have two lone pair of electrons. Or what? Ammonia, maybe. So if you draw the Lewis structure of ammonia, you know they have lone pair of electron. So this is a lone pair of electron, lone pair of electron, lone pair of electron. All right. Or in ions, for example, we have chlorine. So chlorine, if you draw the Lewis structure, you can get 1, 2, 3 minus. So all these are lone pair of uh, electron. So remember, ligands, it should be any in ion or neutral molecule with lone pair of electrons. Okay. All right. Moving forward to the dative covalent bonding. What is dative covalent bonding? Dative covalent bonding is a pair of electrons from the ligand will be donated into the empty orbital of the central metal ion or central metal atom or ion. So dative covalent bonding uh, dative covalent bonding meaning that a pair of electron or a lone pair of electron from the ligand will be donated into the empty orbital of the central metal ion. All right. So this is a schematic diagram showing the combination between the central metal atom or metal cation surrounded by the ligand. The ligand normally is an ion or neutral molecule. The bonding, we call it dative bond or coordinate bond. Okay, so we have a ligand surrounded, and then we have a central metal species, the metal atom or metal cation. Uh, Here is the counter ion. Counter ion is to neutralize the complex ion because the combination between the metal in the ligand, we call it metal ion. So it's overall, it can be It can be complex ion. It can be positive or it can be negative. So the complex ion uh, must can neutralize by the counter ion. So why I said complex ion can be positive and negative? In some cases, we can have ligand, uh, metal, ligand, ligand, ligand in the negative charge. So the counter ion is positive charge. So this one is wrong. It should be N minus. So this one is complex ion negative charge. This one is complex ion with positive charge. All right. So moving forward, complexometric titration is the titration technique using complexometric technique. A dose reaction in which sample metal ion is transformed into the complex ion by addition of complex agent. We call it agent. So if we have a metal and combine we have a ligand, so the metal in the ligand will form the complex ion. So this is the titration by using complexometric technique. All right. Complexometric technique, as I mentioned just now, is a titration method based on formation of complex due to the reaction between the metal atom or metal ion, which is cation, in the center, surrounded by the complexing agent. We call it a ligand surround it. The ligand can be an ion or neutral molecule. Complexometric titration are particularly useful for the determination of mixture of different metal ions in a solution. Okay, normally we use the complexometric technique because we want to determine the mixture of different metal ion in the solution. Okay, in complexometric, two things. We have a metal cation in the center and also the ligand surround the metal ion. So ligands can be classified according to the number of bonding site that are available for forming the coordinate covalent bonds to the metal ions in the center. So the types of ligand can be classified as monodentate ligand. What is monodentate ligands? Is any ligands have only one binding site. One binding site meaning that it only has one lone pair of electron that can be used to form the coordination covalent bonding. For example, we have chlorine, bromine, or ammonia. So this is a common of monodentate ligand. We have a water, uh, amine, ammonia. Okay, this is an example of monodentate. In here also example of monodentate in the anionic form. All right, we can have cyanide, thiocyanide, hydroxides, or all the group 7 compound, chlorine, bromine, iodine. Okay, another class of ligand, we call it bidentate ligand. Uh, Bidentate ligands is the ligands have two bonding sites, meaning that it has two lone pair of electron that can be used to form the coordinate covalent bonding. So the common example of bidentate ligand is ethylene diamine. Polydentate ligands is the ligands have two or more lone pair of electrons is the bonding site. The common example is EDTA, ethylene diamine tetraacetic acid, which has hexadentate ligand. Uh, it has a 6 point for the bonding site. So this table gives you several example of monodentate, bidentate, and also polydentate. Another kind of ligands or complex ion is chelate. So chelate is a chemical compound in the form of ring. Okay, in the form of ring that contain metal ion attached by coordinate bonds to at least two non-metal ion. So the ligand in the ring structure, we have a crown 6, uh, crown 4, or dibenzo crown 6. So this is example of chelate ligands, crown ether. So what is a chelate? Chelate when the polydentate ligand, polydentate meaning that binding sites more than two, coordinate with metal ion in forming cyclic or ring structure. So the keywords are for chelate, it must have cyclic or ring structure. The complex that form, we call it chelate. The chelate is the chemical compounds composed of metal ion and chelating agent. So meaning that the chelating agent uh, uh, have coordination binding site more than 2. Okay, chelate when the resulting uh, complex ion with ring structure. Okay, all right. So, chelating agent or chelating agent. A chelating agent is a substance whose molecule can form several bonding to single metal ion. In another word, the chelating agent is multi-dentate ligands. Example of chelating agent is ethylene diamine. Okay, so this one is ethylene diamine. The ethylene diamine, CH2, CH2, NH2, and H2. So the binding point is the amine in the nitrogen side. Okay, EDTA is an example of polydentate ligand. It has 6 binding sites. EDTA is the ethylene diamine tetraacetic acid. It is a versatile chelating agent. It has, as I said just now, it has a 6 hexadentate ligand. It can be formed 6 bonding with metal ion, or it can has a 6 binding sites. It can be symbolized by H4Y. H4Y, the symbol of ABTA. So this is the chemical structure of EDTA. Ethylene diamine. This one is ethylene diamine. CH2, CH2, N, and tetra acetic acid. Acetic acid is the uh, CH3O minus. This is acetic acid. So we have tetra, meaning that tetra is contained of 4 acetic acid. So as you can see, the chemical structure of EDTA is ethylene diamine in the center with 4 acetic acid connected to the ethylene diamine big point. Okay, so the 6 binding site is 1, 2, 3, 4, 5, and also 6. All right. In addition to the four charge site in the carbonyl group oxygen, this is the four charge of carbonyl group. This is carbonyl, 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 carbonyl. The four charge 1, 2, 3, 4. The four charge site in the carbonyl group, each of the two nitrogen also has unpaired of electron, making 6 pair available to form the covalent bonding. Uh, in forming a complex example with calcium ion, this is a complex of calcium ion, Ca2 plus. All 6 bonding sites bond to calcium, forming large aggregate consisting of single ADTA ligands wrapped up around the calcium ion. So this is the another presentation of chemical structure for the ADTA. Ethylene diamine. This is ethylene diamine, CH2, CH2, N, tetraacetate. So the first tetraacetate, second tetraacetate, to third tetraacetate, and the last one tetraacetate. So the binding site is 4 in the carbonyl group, 1, 2, 3, 4. And also the binding site is the unpaired electron of nitrogen. Unpaired electron, we call it lone pair of electrons. So this is showing how the calcium ion binded with the ADTA. So calcium ion in the center is binded by 6 binding site of ADTA. So first binding site, second binding site, third binding site, and also fourth binding site. And also the nitrogen can bind the calcium ion. So it has 6 bending site, exa bending site for the EDTA. Okay, what next? So this is a schematic diagram to showing any metal cation can be binded with the EDTA. In this case, it's calcium ion, but we can bind with another metal cation. Okay. Complexation titration is commonly the analyte The analyte, the chemical in the Elin flask is the metal cation, and the titrant normally is the ligand. So this is metal cation. The titrant in the beurets normally is ligand. Titration process buffer the solution at suitable pH, add the indicator, titrate the metal with suitable complex ligand. So again, for forming the complexation titration, the first one, you have to buffer the solution at the suitable pH, add the suitable indicator, and then we titrate the metal ion with the suitable complex ion. Okay. EDTA is titrant or complexing agent in the form of sodium salt of the ethylene diamine tetraacetic acid. The EDTA, in order to be titrant, is in a salt form. So the EDTA combined with sodium salt. One-to-one reaction between EDTA salt and metal ion. EDTA ligand will bind strongly to the metal ion. It is pH dependent, and the repeat reaction is complex, is stable. So EDTA disodium salt. What is EDTA disodium salt? Just now in A2, the EDTA are present in salt form. So we use sodium ion. So what is EDTA disodium salt? It is a usual source of EDTA for use in the metal analysis. Why we use EDTA, there is sodium salt in titration and not in the acid form. EDTA disodium salt is more soluble compared to the acid. Why we need a soluble ligand? Because we need to replace the sodium ion. We need to replace this during the titration. This sodium ion will be replaced by metal cation, which is the analyte in flask. Okay, the anemia. plus. Okay. So we need to replace the in A. So the EDTA should be soluble. Since EDTA is a weak organic acid, it dissolves slowly in water. So why is the structure of the sodium salt of what is the structure of disodium salt of EDTA? Okay, if you still remember, the structure of EDTA is H4Y. Now we add on Na2, so it is Na2H2Y. All right. So dissociation of EDTA. EDTA is frequently symbolized as H4Y, and the EDTA salt is Na2H2Y, where Y is this chemical compound. Ionization of H4Y, EDTA is depending on the pH. If pH will 1, so it will be ionized to dissociate one proton, so it become H3Y minus. So the ionization can be continuously happen. So ionize another ion, so leave it H2Y 2 minus. Another H plus, so it become H3 minus. And ionize further, it pH 10, so all the hydrogens is already ionized, 4 hydrogen, so it leave it Y4 minus. Okay, so the exact position of the equilibrium is controlled by controlling the pH of the solution. At pH 10, Y4 minus is predominate. At pH less than Y, less than 1, the EDTA form H4Y will be predominate, meaning that it's no dissociation yet. The multidentate or polydentate ligand normally is forming 1-to-1 mole ratio with the metal cation. The metal with the ligand is 1-to-1 reaction. So for example, if one to determine the amount of calcium cation by using EDTA is 1-to-1 mole is 1-to-1 mole ratio. So the reaction occur in a single step. It gives a sharp change in the metal ion concentration at equivalent point. And metal ion is either totally complex. The metal ion in this case is calcium, is either complex, totally complex, or no reaction between the metal ion and ligand at all. So it is two situations. It's complex 100% or no reaction at all. Okay. So in the titration, we have the equivalent point in the end point. So what is the end point for EDTA? So the end point is to tell us is the you have to stop the reaction, or you have to stop the titration. That is the end point. So the endpoint for EDTA titration, metal ion internal indicator, metal ion internal indicator, we call it EBT. EBT is aerochrome black T. EBT, aerochrome black T. That is the internal indicator. So EBT, aerochrome black T, is the organic dye indicator that form color chelate with the metal ion. So the complex are often intense colored and can be detected by using the naked eyes. Or we can detect the endpoint using the ion selective electrode. Ion selective electrode, it should be sensitive to the analyte that you want to determine in the analysis. Okay. EBT, aerochrome black T, is the internal indicator, as I mentioned just now. EBT function similar is the acid-base indicator. Useful is the indicator for metal ion only in the pH range in which competition with the proton is negligible. So EBT can be symbolized H3IN. In acidic in moderate basic solution, the predominant acid-base equilibrium exhibited by the indicator is follows. So the EBT H3 ion is an acidic form. Normally, it's red in color. So when it ionized, it can form still red in color. And then at the moderate basic solution, it change from red to blue. So we can detect the color changes. Or at the strongly basic solution, pH more than 10, it can turn to orange. So from acidic red, basic, moderate basics is a blue, very basic or strongly basic solution, it become orange. All right. So this is showing the color transitions of the solution have the internal EBT is indicator in the acidic and also in the basic. So one drop difference of 0.01 molar of EDTA between the first and the second pictures, between the second and the third. So this is only one drop different. You can see the color changing very significant. All right. From it's about red, around red color, up to the blue color. Okay, the metal complex of EBT and a chrome black T are generally red in color. To observe a color change with this indicator, it is necessary to adjust the pH to 7 or above pH 10. So the blue form of the indicator will be predominant. Okay. When the titration begins with the metal cation and the EDTA, the endpoint reaction is then at pH 10. At pH 10, the EVT, the indicator will be changed from red into blue. Therefore, the end color change is from red to blue. So the endpoint reaction reach at pH 10, which is EBT in blue color. If the pH is below 7, then the color change is from red to red, which is very impossible to detect the endpoint color. So if the pH 10, the endpoint color is from red to orange, which is it's not sharp. We cannot really differentiate between red and orange color. So it's not enough to detect the color changes. Limitation of EBT, the solution decompose slowly. The limitation of ABT is that its solution will be decomposed slowly. So EDTA commercial usage. Normally EDTA used in the soap or detergent is a complex with calcium and magnesium ion. So in the soap or detergent, the EDTA will be either is a ligand. It can be formed complex with calcium and magnesium ion. This ion, which are hot water, are bound to the EDTA and cannot be interfere with cleaning action of the soap or detergent. Also, EDTA can be used in food. Certain enzymes are responsible for food spoilage or food poisoning. The EDTA is used to remove the metal ion from this enzyme. Used to promote the color retention in dried banana, beans, chickpea, canned clams, pie filling, frozen potatoes, or canned shrimp. Used to improve the flavor of retention in canned food, carbonated beverage, beer, salad dressing, mayonnaise, margarine, and sauce. It inhibits. So the EDTA inhibit the rancidity. It avoid the rancidity in salad dressing, mayonnaise, sauce, or salad spread. Okay, I think that's all for this video. We will continue the next video on the water water hardness. Okay, thank you. See you again on the next video. Okay, bye bye.